Normal approximation to binomial. Remember that binomial distribution is only discrete and normal is continuous. And so suppose we have a random variable x that is binomial with the parameter n and p. This means there are n trials and the probability of a success outcome is lowercase p. Suppose further that n times p is at least 10. This is the number of trials times the probability of success. The product is at least 10. Also, n times 1 minus p. This is the product of the number of trials and the probability of failure, 1 minus p. And this is, suppose it is at least 10. If both of these conditions are satisfied, then we can use the normal approximation to compute the binomial probability. What that means is that we use a continuous distribution. A continuous probability distribution has a density curve and it is normal, so it has the bell-shaped curve to approximate the discrete random variable. Now, for the binomial discrete random variable, x can only take on the discrete values such as 0, 1, 2, 3, 4, 5, counting numbers that we can put in orders. So for example, these are 0, 1, 2, 3, so we pick 1 and just label it k for now. If we're looking for the probability of x equals k using the binomial distribution, then this is n choose k, and it's the number of trials total, and then the probability of success raised to k power, the probability of failure 1 minus p raised to the remaining n minus k. However, by doing so, sometimes if we need to do it by hand, this number is very large. So instead of using the discrete random variable binomial, we'll approximate using the normal distribution. But every time we work with the normal distribution, then we would need to know the mean. Luckily, the mean for the binomial is computed using n times p, and we also need the standard deviation sigma. The standard deviation is the square root of n times p times 1 minus p. This will be the mean and the standard deviations of this normal approximation. The mean and p and the standard deviation is the square root of n times p times 1 minus p. Remember that the mean is a number from the peak look down. With this mean and the standard deviation, we can find the probability of x equals k using the table or using technology. However, with the continuous random variable, the probability at a single point is 0, and we know that that should not be the case. And so to correct it, we take any value k and then we add 0.5 to it and subtract 0.5 to it to get a thin strip. And so this bar would represent k, one single k. This value is k plus 0.5, and this is k minus 0.5. So for example, if k is 10, then this is 9.5 and this is 10.5. And so the normal approximation for this binomial is the probability between k minus 0.5 less than or equal to x less than or equal to k plus 0.5. For continuous random variable, it doesn't matter whether we use less than or equal or just simply strictly less than. And this is a normal approximation for binomial if we only need to find the probability of exactly k. This is also known as the continuity correction. We correct it to include the value k. The distance or the width in this case is only 1. k minus 0.5 and k plus 0.5 has a distance of 1, and it represents the probability of x equals k. Now, for normal distribution, in many cases, we would need to find the probability of at least, at most, more than, less than, and so on. And so we just saw how we compute the probability of exactly 1 using the normal approximation to binomial. Well, that means that instead of using this formula, the binomial formula, we can set up this so that we can use the table or most likely technology, a calculator. To simplify the following discussion, we will suppose that k equals 23. If we're looking for the probability that we have at least k, again, k is 23, then we would interpret it as p of x greater than or equal to 23. And again, this means 23 or more, at least 23. Using the continuity correction with normal distribution, we always draw the normal curve, the bell-shaped curve. This is 23. Remember that for binomial, it is just simply one single value, but for normal, the probability over one single value is 0, so we need to correct it. And we always add and subtract 0.5 for the correction. And so if we take 23 minus 0.5, we get 22.5. If we take 23 plus 0.5, we have 23.5. And that one single strip of the width 1 represents the number 23. And so the next question is that, do we need to include 23 in this probability? The answer is yes. And also, we need everything on the right-hand side of 23. And so not only we need to include 23, we also need to shade everything on the right-hand side of 23. But since 23 is included, we are going to correct this at p of x greater than 22.5. And the reason why we use 22.5 is because we want to make sure that 23 is in the shaded region, not in the boundary, not at the border of the shaded region. And then we proceed to use a calculator or technology. If we're looking for the probability of more than 23, this time more than 23 is x greater than, strictly greater than 23. 23 is not included, but anything that is more than 23. Looking at this picture here, we want to exclude 23. 23 is not in the shaded region this time. And to make sure that it's not in the shaded region, we're going to correct this as the probability of x greater than 23.5. In this range, noted that 23 is not included in it. And again, this is what we call a continuity correction. What if now we're looking for the probability that x is strictly less than 23? If x is strictly less than 23, then this is p of x less than 23. And so with continuity correction, we know that we have to shade everything on the left-hand side of 23, but also in this range, we need to make sure that 23 is not included. And so if we look at this graph here, how do we make sure that 23 is not included? We only need to go up to 22.5 then. And so with continuity correction, this is simply the probability that x is less than 22.5. In this range, everything on the left-hand side of 23 is included, but it does not include 23.